for the last talk of the session, Andrea will tell us about Verus.
Hi folks, thanks for the intro. I'm Andrea, and today I'm going to talk about Verus and how it verifies Rust programs using linear ghost types. So first of all, let me clarify what I mean by linear types here. And we're talking about linear types as in Rust. So the Rust linear or ownership-based type system and its borrowing extensions. So as you may know, in Rust, if you have a value like v of type vector here, you're not allowed to duplicate it. If you attempt to do so, the compiler will catch it and reject this code. It may be difficult to write code with just these techniques, so what you can do instead is grab immutable references, as many as you want, to a certain value. Or alternatively, you can grab a unique or exclusive mutable reference to a certain value, like in this parameter here to function g. But if you were to try and pass v as both a mutable and immutable reference, again, we will get an error because we will be aliasing this mutable reference with an immutable one. Okay, now that I've clarified this, Rust, as we've seen, has this sophisticated type system that uses ownership and borrowing. And this enables a type-safe, low-level systems code without the need for garbage collection. We believe this is one of the reasons Rust has gained so much popularity recently. However, even type-safe code has bugs, obviously. And sometimes in Rust, people or programmers need to use unsafe to express certain kinds of programs that don't fit in the linear or ownership discipline of the language. So deductive verification is something that can prove deeper properties about code, as you can imagine, and we'll see how that includes for code that would have otherwise have required the unsafe keyboard in Rust that lets us break out of the ownership discipline. So I'll talk about Verus, our new SMT-based tool for verifying Rust code. And SMT here, we're going to use the solver as a semi-automated theorem prover, like other tools of the same family do. But we'll see how SMT verification can also help us overcome the limitation of the Rust type system, and how ownership and borrowing can make SMT verification easier itself. And it does this in two ways. One is simplifying memory reasoning, and the other is using separation logic style techniques. And we're going to go into more detail about those in the talk. We'll do this primarily by example. We'll see how to read and write from pointers in Verus, and we'll use that knowledge to build up a doubly linked list, which you may know is difficult to write in regular Rust. So first of all, though, I want to show you what it looks like to write some Verus. Imagine you're writing an implementation of Fibonacci. You want to verify it correct. You're going to write a specification. So you're going to add a post condition, and you're going to add a functional representation of what the program is supposed to do. And it's what this spec function Fibo is doing. If we run Verus on this program, we'll get this error. Verus cannot prove the post condition. And this doesn't necessarily mean that the post condition is false, it's that we haven't given the semi-automatic tool enough information to prove it. So how do we address this? We're going to need a loop invariant, as in similar tools that you may have seen. And also, we're going to have to address the potential overflow in that addition. And to address that, I'm going to have to add an additional precondition that the result fits in a U64. And I'm going to need a separate proof that I describe here as a proof function. The details of this are not super important. What I want to highlight here is that in this language, we have three different modes. We have exec mode code on the left, the implementation we were trying to write. Proof mode code, which lets us express things like lemma calls and the proof bodies. And spec mode code, which is how we describe functionally what the program is supposed to do. So in Verus, exec mode code can contain proof and spec mode code, and proof mode code can contain spec mode code. So this makes it possible to write programs and proofs in a single language. This is similar to other tools like Daphne F star, where a single language provides facilities for both. And the three modes that we've seen so far, exec mode, proof mode, and spec mode code, are important for linear ghost types. Let me show you how. Exec mode code is the code we want to verify. It's checked for ownership and borrowing. It's regular Rust code that you want to write, and it gets compiled to the final binary. Proof mode code is for lemmas and assertions, and it's still checked for ownership and borrowing, like regular Rust, but it's erased. We don't want it to appear in the binary. And finally, spec mode code, in which we write our functional specification of the program, is a functional language in which copying is always allowed. So we break out of the ownership and borrowing discipline because it's a functional language, and this is an erased mode as well. We don't want it to appear in the binary. So we're going to focus on the fact that proof mode code is checked for ownership and borrowing and how that enables linear ghost types. So Verus, again, uses SMT verification to overcome Rust type system limitations, again, and we'll see how we linear ghost types, and uses ownership and borrowing to make SMT verification easier. And we're going to focus on the fact that it does this by using separation logic style techniques that leverage these linear ghost types. Again, we're going to go through a couple of examples. First, though, let me show you how you read and write from a pointer in regular Rust. We can have a function that allocates a U64 size chunk of memory and gets a pointer. Then we write into that memory. We read from that memory. We deallocate the memory. And then we attempt to read from that memory again. You might notice a problem here. In Rust, we need to mark this block unsafe because we are doing operations for which the compiler is not able to prove safety. And in fact, this is demonstrated by the fact that we are doing a read after free here, so undefined behavior. What can we do in Verus instead? First of all, we don't need the unsafe block. Then we use the PPTR API that we have in Verus, which replaces the raw pointer API, and returns a pointer, which is mainly the actual runtime pointer that can be copied arbitrarily, and a linear ghost permission of type points to here, similarly to here the parallel is to a separation logic points to assertion, if you're familiar. And here in Verus, linear ghost permissions are syntactically marked with this struct marker. So the first important property of what we get back from empty is that the pointer and the permission are associated at the SMT level. So we have an ID associated with both, and we'll see how that helps make sure that we keep them aligned. The other thing we can do is track the value in the memory through the permission. So the permission has a ghost value that says currently the memory is uninitialized. And I should mention the ID I was talking about before is also ghost. It's not something that will appear in the program. So first, let's write into the pointer. We use the put function that critically takes a mutable reference to our linear ghost permission and uses the SMT solver to check that the permission and the pointer are one associated with the other. We are not using a permission for some different pointer. We are using the one that was allocated for this pointer. And this is how we use SMT solving and ownership-based reasoning at the same time to achieve these goals. So once we've done that, we can determine that the value that we have in the memory location is 5. We might read from it, and this time we only need to have a shared or immutable borrow to the permission to be able to do so, and that allows us to take potentially multiple references to the memory location, as long as those are exclusive with immutable ones, or with mutable ones, sorry. And then we can assert that the value comes back that we expect. We can deallocate, as we were doing before, but critically here, we have to relinquish our permission. The API for deallocating requires us to relinquish the permission so that if somebody were to try and read from the memory location using that permission again, we would catch that. And in fact, in particular, it's the Rust borrow checker that catches this mistake. We don't have to go to the SMT solver for this. We get this error very quickly thanks to the borrow checker. And here again, this is enabled by the mode system that I've been talking about. So most of the code is exact mode code, but what I want to point out is that the proof mode tracked annotations is where this tracking of linear ghost permission happens. So when it's initialized, when it's passed by mutable reference, or when it's passed by immutable reference, or relinquished at the end. Okay, so I've shown you a fairly kind of trivial example. People don't really read and write from a single pointer. There's no really real point, but that's to build up to a little bit of a more complex example that hopefully is more interesting. And that's doubly linked lists. You may know that in Rust, it's difficult to write one. And the reason for that is that the cyclical structure of the pointers that you need for a doubly linked list, that doesn't work well with the ownership structure in Rust. So what can we do instead in Verus? Well, we're going to add a linear ghost field to the doubly linked list data structure. And this is, again, a ghost field, but it will be treated linearly. And that will store a flattened representation of all the permissions we need for all the fields, for all the elements in the doubly linked list. How do we access the list? Let's say we want to access the list from the head. We're going to read the head and access the permission that we need, that gives us the ability to read from it. And this operation would repeat to access the further elements in the list. Okay, so we have seen how linear ghost types lets us represent memory permissions and express programs like doubly linked lists that would have required unsafe in regular Rust. Linear ghost permissions also, or linear ghost types, also allow more interesting programs, which I don't really have the time to go through in the talk. They can reason about interior mutability, for example, and this is a situation in Rust where the contents of a certain data type X can be modified when we only have a shared reference to it. And this is complicated by the fact that in our VC generation for efficiency, immutable reference is always treated as immutable. Linear ghost types, with the techniques that we've seen so far, also helps us deal with that. And there's other techniques that we can employ to implement things like memoization behind an immutable reference. And more details about this are in the paper. Additionally, linear ghost types also enable more sophisticated techniques for reasoning about shared memory concurrency. The details are way too much to go into the talk, but the high-level idea is that this lets us write protocols that allow different parties, different threads to exchange these permissions that we've seen so far, and that allows us to implement things like concurrent FIFO queues, thread-safe reader-writer locks, and things like this, and bigger, more complex concurrent systems. The techniques that this builds on are also reported as part of previous work on linear Daphne in this OSDI paper that I'm mentioning. There's also going to be a talk on Friday by Travis Hance on the separation logic underpinnings of some of these techniques. So I presented Verus and how it verifies Rust programs using linear ghost types. We've seen how SMT verification can overcome the limitations of the Rust type system. And now ownership and borrowing can make SMT verification easier by using separation logic style techniques with linear ghost types. And also, and I didn't have the time to go into detail in the talk, by simplifying memory reasoning. In addition to this, Verus focuses on efficient, lightweight verification condition encoding. We want to make sure that Verus is able to scale to extremely large programs or to very large programs. And for this, we need to make sure that the tool is fast, responds fast, and lightweight encoding is critical for that, alongside the simplified memory reasoning afforded to us by the type system. And finally, in the paper, you'll find that the formalization that talks about the mode system, how it interacts with lifetimes and with first-class functions, and how permissions mediate access to the heap. Finally, Verus is open source. You can find it on GitHub. It's actively developed. The author list you saw at the beginning is only a subset of the people that are working on it right now. We have a getting started guide, so if you want to try it out, I encourage you to go on that website and you'll find the guide. And with that, that's all I have. Thanks for listening.
Thanks for a great talk. Did you encounter any uses of unsafe code that you couldn't translate into the sort of track permission system where maybe the ball checker still is too restrictive sometimes to express that?
That's an excellent question. I don't think we have found situations in which there were things that you could express with unsafe that were related to the ownership structure. What we cannot represent, because we focus on safe Rust, is interactions with things like hardware, like memory mapped registers. Those are things that we need to axiomatize and then access through a safe API. But I don't think we've encountered situations in which something you could write in unsafe but you couldn't then translate to our safe API, although the techniques for shared memory concurrency require sequential consistency. So if you're doing more fancy log-free things, those might be harder to express.
Hi, I'm Al Ahmed, Northeastern. This is really nice work. I was wondering if I sort of have a two-part question. I'm wondering if you're familiar with the L3 work that we had with Greg Morissette and Matthew Fluid back in like 2005, 2007. We had capability types in that work where, the capability essentially allows you to think about, strong updates in a safe manner. And your linear ghost types seem very much like the capability types. And we even showed the connection to separation logic. But what we could not do there, because at the time borrowing was not a thing, is handle immutable borrows. So I'm wondering if you have a different predicate from your linear ghost type, which is somehow maybe fractional capability or something that you use for immutable borrows, because
I'm not sure I'm going to be able to answer your question exactly because I'm not that familiar with that work you mentioned.
L3, yeah.
But the relationship with capability is definitely apt. And what I can say is that our understanding so far is that the linear type system in Rust with the borrowing is, if you wish, a different interface to separation logic. So
Completely agree.
So instead of needing fractional permissions, we rely on the substructural nature of the Rust type system and how multiple immutable references are kept exclusive from mutable references. And so we kind of use the logic that Rust provides.
But don't you need to reason about the many immutable references? Because those are not linear, right? You can have many immutable references.
You can totally have...
Immutable is separate from mutable, but...
Absolutely, but the immutable reference in the absence of interior mutability do not allow mutation, so we can just treat as functional values.
You can ignore it.
That's the trick. We can just treat them as functional values. And in fact, I guess broadly, safe Rust is kind of a functional programming language in disguise.
Absolutely.
You can treat it.
Yeah.
Thanks for the
L3
question.
shows that too. Thanks.
Thanks.
I have got many questions, but I will ask 3 if I'm allowed.
Okay.
So the
Ready.
Okay, I'll only ask one then. Do you use? Do you prove functional properties or just safety of unsafe code? And one little one attached. Do you infer the specifications or do you write them by hand?
Great questions. So Verus is designed to prove full functional correctness of large system software. So I went into the details of how the techniques enable having type-safe access to memory, for example, but the overall goal of the project is to verify large system software and do full functional verification. So verify the correspondence of a large program to a small specification. And to answer the second part of your question, that small specification is something that we expect the user to write by hand. And so we don't infer them. We say if you're verifying a key value store, you're going to have to write a small specification of what a key value store is supposed to do. And then our goal is to provide a proof that the implementation matches that specification.
I want to prove that your W-linked list is okay. Do you need the user to write a specification or can you infer?
We ask the user to write a specification, the semantics of the W-linked list. How you'd be able to infer a specification is an interesting question, but not our focus so far. Thank you.
Okay, let's thank Andrea again. And let's enjoy lunch.